All right, so let's consider a rigid body. Maybe this is someone you killed a few days ago. No, just kidding. That's disgusting. Who said that? A rigid body, or rigor mortis. Okay, never mind. All right, so we've got a rigid body. It goes from 30 RPMs. You'll see this sometimes, RPM, revolutions per minute, to 2,500 revolutions per minute in 4 seconds. So this could be, I don't know, this could be the engine of your car. Maybe some of you have a tachometer in your car that tells you the rate your engine is spinning. If your engine is idling, maybe turning at 30 RPMs, and then you hit the gas and you rev your engine and it picks up a big speed and it starts to spin really fast, 2,500 times around per minute, and it only takes 4 seconds to get up to that speed. Okay, so based on that, we're going to answer some questions. This will help you with your homework. So we'll break this into some parts. Okay, so first part, what is alpha? What is the angular acceleration? Now, you got to be really careful if we're looking for linear or angular variables. In this case, we're given an angular variable. Okay. So let's think about what we've been told. We've got some different variables here in the problem, and in a sense what we're doing is we're writing our knowns out. We've got a rate of rotation before and after. So what we have an initial rate of rotation, omega naught, 30 RPMs. And I have to be a little careful about this, 30 RPMs, 30 revolutions per minute. I need to get this into base units. So the first thing I'll do is I'll change revolutions. Revolution is equal to 2 pi radians. So I'll multiply by 2 pi to get radians per minute. And then I'll change minutes to seconds. 1 minute, 1 minute is 60 seconds. So I'm going to multiply by 2 pi and I'm going to divide by 60. And I'm going to get, well, I can just do this in my head. I'm going to get pi radians per second. So the initial rate of rotation is 3.14 radians per second. Okay. And then we've got 2,500. So my final rate of rotation, omega, we could do the same thing. We'll multiply it by 2 pi. We'll divide it by 60. And this rate of rotation, 250 revolutions per minute, or rotations per minute, is going to turn into 260 radians per second. So we have an initial and a final angular velocity. The other given variable is time. So omega naught, omega t, we're looking for alpha. So this should seem very familiar. This is like listing my knowns out. We're solving for an acceleration. So we'll go to our kinematics equations, this time the angular version. And this is the equation that relates the 3 known variables with the 1 unknown variable. As long as I'm in the proper units, we can solve this then. So 260 radians per second is the final. Pi radians per second is the initial. And the time is 4 seconds. So 260 minus pi divided by 4 gives me alpha. The rate at which this object, say your engine of your car, is gaining rotational speed is 64 radians per second squared. So every second it spins 64 radians per second faster. Okay. For the second part of this problem, my second trick of the evening, okay. How many rotations has it made after 1.5 seconds? So not the full 4 seconds, but after 1.5 seconds of rotating, how many times has it gone around as it gains speed? So it's not a constant angular speed. This is accelerating, and so I have to take into account that acceleration using my kinematics equation. Now if I think about the knowns, if I look up on my page here, I've got an initial, a final, a time, and now I also have alpha to add to my list of knowns, 64 radians per second squared. And now we're looking to solve for how many rotations it's gone through, or theta, the angular displacement. So to find my angular displacement, I could use this kinematics equation. Theta equals theta naught plus omega naught t plus 1/2, alpha t squared. And we know all of the variables in here besides theta. Okay, it doesn't matter. We get to pick where the 0 position is, so we can start our object off at an initial angular position of 0, and then solve for what angle it rotates through during this time period. Okay, so my initial angular speed was pi radians per second. We're going to rotate for 1.5 seconds. We already found our angular acceleration was 64 radians per second squared. Again, 1.5 seconds quantity squared. So now we can solve this for theta, how many times or what angle this will rotate through. And when we get an answer for theta, theta in this case ends up, plug this in my calculator, got 77. So this rigid object will rotate through 77 radians in 1.5 seconds as it accelerates, as it picks up speed. But I'm asked how many rotations it makes, so I have to do a unit conversion here at the end. And one rotation or revolution is the same thing as 2 pi radians. So I have to take 77 divided by 2 pi, and I find that this thing to the nearest rotation has made 12 rotations. My engine has spun around 12 times in 1.5 seconds as it picks up speed. So 2 more parts to this problem. We did part B, so we got part C now. Let's look at a linear variable. Everything so far we've done is angular. Say, how fast is a point 50 centimeters from the axis of rotation moving after 4 seconds. So this thing's picking up speed for 4 seconds, and once it's hit this speed, the whole thing's spinning pretty fast. But different points on this object are spinning different speeds because they're different distances from the axis of rotation. They all have the same angular speed, but they have different linear speeds. So here we're looking for a linear speed. So the linear variable is equal to the radius times the angular variable, and from this we can get a tangential speed of this object. So it's 50 centimeters or 0.5 meters away from the axis of rotation. And from the givens in this problem, we know that this thing after 4 seconds is traveling at 260 radians per second. So we're going to multiply a half times 260, and we find that this point's moving 130. And again, a radian isn't actually a unit, it's just a ratio of 2 lengths, so I can write this as 130 meters per second. So this point, half a meter away from the axis of rotation, is moving really fast, right? A couple hundred miles per hour, or 130 meters per second. Okay. Final part of this problem, let's take a look at an acceleration question, specifically 2 different types of acceleration. Say, what is my total acceleration of that point? So you got to watch out when you're finding an acceleration of a rotating object, especially one like in this problem. It's turning, so there's a centripetal acceleration, but it's also gaining speed, so there's a tangential acceleration as well. So let's see. So total acceleration by the Pythagorean theorem is going to be my tangential acceleration squared plus my radial acceleration squared. We'll take the square root. And my tangential acceleration, well, I can get that by multiplying the radius by the angular variable. So r alpha is my tangential acceleration. And my radial acceleration, my centripetal acceleration, is r omega squared. So I've got r omega squared quantity squared, and we derived that before on a previous page. Okay, so I've got to take into account both types of acceleration in order to find the total. So in this case, we know what all these values are, so we can solve for it. So the first term, half a meter, 50 centimeters. Alpha was 64 radians per second squared. So all of this is my first acceleration. This is my tangential acceleration. So I got to square that. And then we'll add to that 0.5 meters times omega. Now this is, at this particular point, this thing has now reached a speed of 100, let's see, 130, no, it's 260 radians per second. That's right. So 260 radians per second after 4 seconds. And so, you know, actually this is interesting. This term, this centripetal term, is changing as time goes by, as it turns faster and faster. So after 4 seconds, this is its angular speed. And then that will give me my centripetal acceleration, my radial acceleration. I'll have to square this. So this is a big mess, right? But we got to use this to find the total acceleration of the object. And we go to find the total acceleration of the object, and we get a very big number, 33,800 meters per second squared. And that's a combination of translational, our tangential and radial accelerations happening at the same time. That's the end of our lecture on angular kinematics. Takes us to the end of things, and basically all of what you need to know from Chapter 8. So go ahead and try some homework, and hopefully through homework and lab work we'll get a chance to practice this and make sure we really get it. Once we have angular kinematics down, then we can kick over to angular dynamics and look at the causes of angular motion. See you next time.